I hope that you enjoyed the coffee break. So our next one is Daniele Taufer. He's going to talk about the additive decompositions of symmetric tensors with and without schemes. So
thank you. Thank all the organizer for having me here, and thank the. I guess I should thank the network because this talk is based on 2 different works with people from the network, from the panels. First one is joint work with I guess. Okay, so thank you for your attention. So apparently for next speaker, if you push the middle button, it's finished. So as I was saying, it's based on 2 joint works, one with Enrica Barilli, Costa Rica, together with Bernard Morin, who will come tomorrow, I guess, and Oriol Reich-Pite, with this. Okay. So I will. This will be a broad talk. I will first give a bit of an idea of how we consider schemes, starting from decompositions of polynomials or symmetric tensors. And then, as the title promises, I will also try to do the same, but without schemes. I know people don't like schemes. They should like the second half of the talk. So what is a generalized additive decomposition? It starts from a degree D form, so a degree D homogeneous polynomial, which you may see as a symmetric order D tensor. A generalized additive decomposition is an additive decomposition, which involves some linear form. So now let's try not to finish the slides again. Some linear form, Li paired with some omega I. The only requirement that we ask is that the linear forms are pairwise not proportional. That would be relevant for the scheme theoretical aspect. And that the Li does not divide omega I. This is not restrictive. If it does divide, just collect more exponents in the Li. These forms, as far as I know, they were introduced in this work, in this book by Yerudin and Kanev, but they have been around since a while. And this is just an intuition, a tensor intuition of this guy. So the idea is that we want to represent these homogeneous polynomials by so these symmetric tensors by using lower order symmetric tensors. I will not comment much on the utility of this, but clear way to this is clearly more efficient, right? Instead of listing all the possible monomials in any representation that you like, you can do it better if you know how to decompose a polynomial, hopefully with a small number of terms. And this problem has a geometric interpretation. So so the Worrying decomposition problem has appeared already many times during these 2 days. Asks you to decompose a form by using only powers of linear form. In general, we can generalize this problem by asking to decompose the form by using some power of linear form that still has the same geometric meaning, so that will represent the point and a point on the Veronese variety. But also, we attach something that may have positive degrees, so it's not only a constant, and that will describe some oscillation to the Veronese variety. So those are called oscillating varieties, as they have been studied previously, for example, from Alessandra and others. But yeah, many of the previous works were like, let's fix K, and let's look at the span of K's oscillating varieties. So in this work, we don't fix K. So any term can really have different degree. And as a small one-up, those varieties you can compute easily the dimension. They are nested one inside the other, and at least for small K's, this nesting is really representing the singular locus. So the singular locus of the OK's variety is given by the previous one. This is not true if you go beyond the half, but okay. And this is a very stupid observation: is that ODD is really the ambient space. You can always write any polynomial by L to the 0 times the polynomial. This looks stupid, but that will play a role in a second. So this is just a trivial way to say that GIDs, so those decompositions, there are infinitely many of them, and it's very easy to come out with some decompositions. Of course, some will be better than others, and this work will be about finding the best ones. And the final geometric interpretation, as I said, this is somehow you may think of a generalization of the Waring decomposition problem. So instead of spanning F by powers of linear form, you can also use tangency directions or higher osculating directions. The algebraic toolkit that we use is a polarity. So there are several versions of a polarity in the literature. I will try to connect all of them, which we may or may not result in a complete mess. The most famous one is the derivation. So I denote by circ the derivation axiom. So y to the beta circ x to the alpha is just the derivation beta times, where beta is a vector of x to the alpha. And the contraction is really the coefficients-less derivation. So it's really the same operation, but without coefficients. And if your field has characteristic 0, you may easily see that the algebras generated by those two axioms are the same. And we look at the annihilators of those actions. So we look at forms in R. So R will be our dual ring. So the ring R will act on S. We look at elements of R that kills F by derivation if it is uncirc, or contraction if it is uncontract. And the algebraic reason why we like those type of decompositions and not like completely random other types of additive decomposition is that they correspond canonically to schemes. So in fact, we have this is my version of an extended apolarity lemma. Apolarity lemma is a little bit different in the literature, but morally this is it. So this lemma says that you can find such a decomposition if and only if you can find an ideal which defines points inside this annihilator. So an ideal that is defined by forms that kill F by derivation. And this ideal, it defines points, so it's zero dimensional in a projective sense, and it has components that are not too long in some direction. And so what I want to stress here is that this is a little bit annoying, but it's a personal battle of mine. So the fact is that this is a one-way construction. So if you give me a generalized decomposition, I can cook up, in fact, your computer can as well, cook up the scheme corresponding to the polynomials defining the ideal of the scheme with this correspondence. But if you give me the scheme, in general, I cannot tell you from which GID this comes from. So this is really generically a one-way construction, and this construction is very effective. In fact, you can, for example, if you don't want to bother yourself, you can use the programs we implemented with Alessandra and Alessandro in a recent work. And everything it uses is linear algebra, but an homogenization of an ideal, which is not, strictly speaking, linear algebra. And all this construction is based on this very important result of Jarek and Veronika Buczynski, who proves that so the construction itself works for any GID, but if you look at minimal ones, so those that minimize the length of the associated scheme, or in algebraic terms, the degree of the polynomial, those you may restrict yourself to look at only Artinian-Gorenstein schemes. And those are precisely those that are hit by this construction. So this construction somehow, it's good candidates to be minimal schemes. The way we measure a decomposition is exactly by the length of the associated scheme. And we call the GID rank, or the GAD rank, the minimal size of a possible GAD of F. So there is a huge space of possible decompositions of F of this type. But of course, to each of them, there is an associated natural number, which is the length of the scheme. We want to find those decompositions which minimize this length. So just to be very concrete, in the case of Waring decomposition, this will be a scheme of reduced points. So every point will have weight 1. So the length of every point will be 1. So minimizing the length of the scheme is exactly the same as minimizing the number of points. But in general, those schemes will be non-reduced, so they will have multiplicity that you want to count. And here is an example. So you are given this, you are given a polynomial like this one, and you want to compute the minimal additive generalized additive decomposition, and you hopefully want to certify that's the minimal one in fact. So we will work. We need to work in a affine chart. So we need to dehomogenize our projective setting. So with the prime, I will denote the affine chart. So the dehomogenization. For the sake of simplicity, you can just think of just put x0 equal to 1, and the construction. We construct this dehomogenized f by just start from your form, construct the divided power form, which is just the same form but just scaling the coefficients with some scalars, and then you take L equal to 1. So in the easy case, you can take, have in mind L will be x0, so you just take f, change the coefficient a little bit with some binomial or multinomial coefficients, and then put x0 equal to 1. This construction gives you an affine polynomial. If you start from an homogeneous one, but then you dehomogenize, you get something affine, but the degree will be bounded by the degree that you had before. And we call inverse system the set of all the possible contractions, not derivations, of this polynomial here. So this guy here is the ring, is the affine ring acting on a affine form, and you dehomogenize. You contract in every possible direction. So you contract with every linear form, with every degree 2 polynomial, every degree 2 polynomial, and so on. So you contract with everything you can. You collect all the contractions that you got, and you consider the vector spaces spanned by those guys, and you want to understand the dimension of this vector space. So in fact, we have this lemma that somehow is very well known in our community as the Macaulay correspondence, which says that the length of the scheme, so everything that I said on the scheme theoretical side, can be understood as the dimension of this vector space. So if you start from F, you can either construct the scheme and measure the scheme, or you can construct this FL, take all the possible contractions, this is linear algebra 100%, and then compute the dimension, which is again linear algebra. And so this is an example of the two ways you can look at this problem. You can either construct this idea here, and you look at the Euler function is 1, 3, 4, 4, 4, so the length is 4. Or you can take all the contractions, and you see that they are all independent, those I wrote, and the dimension that will agree with this the final value of the Euler series. The way we use to compute minimal generalized additive decomposition is this Henkel operator, which is the operator that associates to every element, to every linear functional phi that lives in a R dual. It associates this operation here that starts from the ring and lands to the dual, and star multiplies your operator by the form you have as an input, where the star multiplication gives you another operator, and the action of this operator is the same as your previous operator, but you pre-multiply by the form that you are considering. So the goal is to define such an operator such that we can see the ideal of the scheme inside the kernel of this Henkel operator. And this, by the way, will be the same operator, I think, as the moment metrics that we have seen in many talks, mostly from the physical side. How do we define this operator? It's again a little bit dirty, so you need to change to work a little bit with the coefficients. So you start from we do it degree by degree, term by term for the decomposition. So you start from a local term, so omega L to the d minus k. You change the coefficients to omega by adding some factorials that needs to take into account the action of derivations, and then you multiply this affine this affine for polynomial that you found by e to the L, so the exponential series localized in L. And this will be an infinite series in x0, xm, which you can see as a function on R star. And that will be the operator phi that realizes the magic. And all this construction seems completely unrelated to this FL that we saw before. But in the work with Oriol, we proved that, in fact, those two guys are exactly the same, just in two different languages. So if you take this strange coefficient shift in the omega, and you express it in divided power, you get precisely the FL that you constructed from the algebra side. And not only that, but if you take the star annihilator of phi, so it's another annihilator, the third one we see today, which is the kernel of the anchor operator of phi. This will in fact gives you the same ideal defined scheme theoretically. So end of the story, three different ways to see a polarity, but in fact, if you do stuff correctly, they evince the same scheme. The last part of so this will this is a small advertising for Erika's talk. So if you attend the Erika's talk on Thursday, you will see more on how in fact we computationally find those schemes. And in the very last part of the talk, I want to talk about how to find minimal local GIDs, which is a problem which was considered by Alessandra and Oriol previously. So local means you just find the GID but with one term. And this looks like a factorization problem, but it's not. So the parameter space is Pn. Every point of Pn gives you one scheme from F, and this is really one-to-one correspondence. And the way we propose to do it is a bit naive, but I will try to convince you that it works quite well, at least in the small cases. So we construct symbolically this inverse system. So I'm late with the time, so I will be fast with this construction, but you can ask questions here or later. So we construct symbolically this FL by starting from a symbolic linear form L. We stack all the possible contraction into a matrix. We call this matrix inverse system matrix. And basically, the easy lemma is that the length of this decomposition equals the rank of this matrix. So basically, minimizing the length, so minimizing the composition is exactly the same as minimizing the rank of a symbolic matrix. And I want to jump to the example because it's more clear. So you start from an F, you construct this FL, which is the first line that you see, and then you start contracting with every possible monomial, and you list all the possible contracting here. And now the problem is really how to minimize the rank of this matrix in the parameters lambda. This problem is surprisingly difficult. So even if you are in the local case, which seems like an easy factorization problem, it's not. In this example, you can extract two smartly chosen minors, where you see that, in fact, there are only two possible solutions for the linear forms that you can get minimizing the guy. And those corresponds to minima that has a really different structure as a scheme. So this is just an example to show that even a cubic in three variable may lead to GL inequivalent minima, which is not expected, but a bit surprising as well. We have some theoretical results. So, for example, we bound the length of this possible local decomposition from above, and we prove that when the rank is small enough, then the number of minima supports is finite. And when the number of minima support is finite, we prescribe a way to compute those decompositions. But maybe instead of talking about the computational aspect, let me finish with those examples. So we also try to play with these guys, and we show that even for small examples, very difficult configurations may appear. So the number of minimal support may be 1, and this will be the case discussed by Enrico. When the regularity is low, then you have a 1 minimal decomposition. But it can be finite, but not 1. So this is an example where you have 3 decompositions of length 4, no decomposition of length 5, and all the rest of the generic length 6. You may have infinitely many minimal decomposition. In fact, the one-dimensional positive space inside a two-dimensional generic space. Or you can also have jumps and holes, and you may land to non-generic but still infinitely many, and not minimal but still infinitely many decomposition. So those examples are to show that if you try to understand the geometry of those minima, you can do it with these methods by just computing minors, so determinants of this symbolic anchor metrics. But in general, it's not really clear, not to me at least, what you should expect to get. And even in small cases, you see that you get very, very weird stuff. We performed some computation. We proposed some methods to extract those minors. Yeah, this is. I think this is very much optimizable somehow, and compared to the previous methods, so the eigenvector eigenspaces methods, this is honestly different because in fact the difficulty of the problem is related to the rank and not to the regularity. And in fact, this works in many examples where the other methods that we also discussed in the past that do not work. And it allows to compute the chain until the end. In the example I showed you before, I can really tell you, I can really certify the whole parameter space by the number of minima supports that you get, which is completely out of reach with other methods. Although this is not better always. There are examples where the other method is better. For example, when the regularity is low, but the rank is high. It's very much possible. So no methods imply the other somehow. So even if it is the take-home message is that even if it is a somehow naive approach, that seems to work well, at least for small cases. I would be interested to learn more about what kind of sequences that you get. So can you really get whatever for any polynomial of unbounded degree, or there are like geometrical bounds that prescribe somehow? I don't know. For example, you cannot have holes after a positive dimensional stuff or something like that. And this method can be improved if you know the Hilbert function or higher invariance, like the Jordan degree type of the scheme where you want to land. And the rank minimization methods can still be improved. We propose 3 of them. We compare them. But yes, what we really need is a method that takes into account the structure of the anchor methods. So with this, I finish, and thank you for your attention.
Thank you for the presentation. We have 3 minutes for questions.
So on the olds, the number of the support, I assume that you assume that they are like honest, right?
The
support have to be honest.
what do you mean?
Yeah, the next question was, what do you mean by honest? I mean, you can also add like fake points, right?
The coefficients.
Yeah.
You can, but this is a local decomposition. So you cannot add. So this method works.
You wrote number of support.
What does number of support mean?
So it's not local.
No, so this is the number of minimal support. So there are, in this case, there are 2 points that you can choose as minimal support.
Okay.
So the parameter space is P1, and inside P1 you can choose your linear form as you want. So there is one choice that gives you. Sorry, PN. It's PN. So there is one linear form that gives, in this example, one linear form that gives you a rank 4 scheme. No linear form that gives you rank 5, 2 that gives you rank 6. And so you can try to measure really for every possible choice of L, what do you get? What scheme do you get? And with these methods, at least for the small cases, we can really describe completely. So this is the bound we give in the proposition. So you cannot go more than that. Is when you choose a random linear form, let's say. But yeah, what I find interesting is that even in the small cases, more or less everything can happen. So that's not an easy problem, even local.
So let's move to the next talk. And thank you.